Alrighty, hello everybody. In this video, we are going to discuss the different types of reactions and how can we identify what type of reaction is taking place. Okay, if you take a look at the different images on the screen, those are all indications of chemical reactions that are taking place, right? If something is emitting light, that's an indication perhaps of a chemical reaction taking place. Gas formation is another example, whether it's a color change when you're mixing something, or if something precipitates. If initially you have two solutions and once you mix them, a solid precipitate basically forms. Heat is an example of a chemical reaction that is taking place as well. So there are a lot of chemical and physical changes that indicate that chemical reactions are taking place. And we've discussed previously the difference between a chemical and a physical change. In this particular video, we're going to focus on a few different types of chemical reactions that we can classify as combination. And just as the name may imply, there are two or more substances that are combining to form the product. We have decomposition, and that's when one particular substance is basically broken down into two simpler substances. And then we have single replacements, and we'll take a look at that. There's double replacements, or displacement is another way we sometimes write it. For single and double displacement or replacement reactions, thinking about cations and anions will be very useful, okay? And then we have combustion reaction. When something like fuel reacts with oxygen in air, can we identify combustion reactions? Typically, the products involve water, carbon dioxide, and energy or heat. All right, so let's take a look at the first type, combination reaction. Right? That's when two or more substances, which are basically the reactants, are combining or reacting to form the products. All right, so for instance, you have A reacting with B to form AB, where now AB involves a bond between A and B. So if we take a look at an example of magnesium reacting with oxygen gas, and notice oxygen is one of the diatomic molecules, so it exists in nature as O2, right? And magnesium is a metal in group 2A. Well, when you have 2 moles of magnesium reacting with 1 mole of oxygen gas, it forms 2 moles of magnesium oxides, right? So that's an example of a combination reaction. 2 different reactants are combining to form a single reactant, right? And here's an example of magnesium metal. And when it reacts with oxygen, it basically forms magnesium oxides, right? And notice that the ionic interactions between magnesium and oxygen, right? Magnesium is in group 2A. It's a metal. Metals tend to form cation, and its charge is consistent with the group number, so it carries a +2 charge. Oxygen is one of the non-metals, right? It's in group 6A. It forms an anion with a -2 charge. Right, it needs 2 more electrons to have an octet, or 8 electrons around in its outermost energy level. All right, so that's magnesium oxide. And if you recall, in our last lecture, we talked about balancing chemical reactions. So because magnesium oxide is 1 magnesium per 1 oxygen, if we think of its empirical formula, to balance out the oxygens, we need to place a 2 right here, which means we need to place a 2 right here. And those are basically the coefficients, right? All right, well, that's combination reaction. A different type is decomposition reaction, and that's when basically one reactant, so you have a bond between A and B, it's decomposing into the individual atoms, A and B, or into simpler substances. Okay, so if we take a look at mercury oxide, delta right here is indicating that heat is required, and then it forms liquid mercury and oxygen gas. So that's an example of a decomposition where you have one molecule that is splitting to form or decomposing into its simpler components, right? And here's an example of mercury oxide, all right, which when it's heated, it decomposes into liquid mercury and oxygen gas. Okay, another type is what we refer to as a single displacement or single displacement reaction, all right? Where there's only a single atom or ion that basically replaces an atom or an ion in a given compound, right? So notice in this case, A is, an atom on its own. B and C is a bond between B and C. And then what's happening is that B and A are basically swapping spots, right? So let's think about it for a second. If B is a cation that's positively charged, could A be an anion that is negatively charged? No, right? They're going to have similar charges if they can replace one another. Okay, so let's take a look at an example of zinc reacting with hydrochloric acid to form zinc chloride and hydrogen gas. All right. Well, zinc is a metal, and metals tend to form cations. Okay, but zinc specifically a transition metal. And if you recall, transition metals have variable charges, but zinc is one of the transition metals that will always carry a +2 charge. Okay, well, we have hydrochloric acid, right? Well, that's a polar covalent bond, right? There is a bond dipole that's towards chlorine. Chlorine is the more electronegative atoms. And if you think of them as ions, chlorine carries a negative charge. Chlorine is an anion, is a non-metal in group 7A. Hydrogen is a non-metal in group 1A, and if it loses its one and only electron, it carries a positive charge. Right? So which of the two, chlorine or the proton, would you expect to swap places with zinc? Or would you expect zinc to swap spot with the proton or the hydrogen ion or the chlorine? Correct, yeah, the hydrogen. Well, now if we know that chlorine carries a -1 charge and zinc is a +2, that's why we need 2 of chlorine per 1 of zinc. So that's why the product is zinc chloride with 1 zinc atom and 2 chlorine atoms. And then hydrogen is one of the diatomic molecules. So it exists in nature as H2, so we'll write it as hydrogen gas. Okay, so here's the example. So we have the zinc, the chlorine, the protons. That's basically if we are separating them into ions. We have the zinc, the proton, the chlorine. So if we react zinc metal with hydrochloric acid, they'll react, and you'll notice that hydrogen gas will basically begin to bubble off, and then zinc chloride will form. Okay. Well, what about in double replacement or double displacement reactions? Well, then we think of it as the anion of one compound will react with the cation of the other compound. Okay, if that's the anion of one, then that's the cation of the other compound. Or however way those colors have it, right? But it's the anion of one with the cation of the other compound, right? So we're going to take a look. So they're swapping, right? Let's just say if this is the cation and this is the anion, this is the cation and this is the anion of one will form a bond with the cation of the other. And then the cation of one will form a bond with the anion of the other. So they're basically swapping. Okay. So then thinking about a compound and separating it into ions becomes important. So now let's take a look at the reaction of sodium sulfate. All right, well, it's written as sodium sulfate. Well, we know that sodium is a metal in group 1A. So sodium typically carries a +1 charge. And if we have 2 of sodium per 1 of sulfate, that means that sulfate carries a -2 charge. But sulfate was one of the polyatomic ions that we had to know, right? Sulfate carries a -2 charge. SO4, the overall polyatomic ion carries a net charge. Okay, so we have to think about it. We have to separate them into ion. And then the other component is barium chloride. So now let's think of barium chloride. We have barium chloride. Well, barium is in group 2A and carries a +2 charge. We have 2 chlorines, and each chlorine is in group 7A and carries a -1 charge. So now when the reaction takes place, the cation of one will form a bond with the anion of the other, right? And here's sodium chloride. And then we have the cation of one will form a bond with the anion of the other, and that's barium sulfate. Right? And we just make sure we balance the charges. Sulfate is a -2, barium is a +2. So you need 1 barium per 1 sulfate. Similarly, you need 1 sodium per 1 chlorine. So anytime you get a problem like that and you're thinking about what should the products be, separate them into ions. You have sodium and you have sulfate. And then you have barium, and then you have chlorine. I'm just writing both so you know why it's BaCl2, right? So then when you're predicting the product, the cation of one with the anion of the other, that's basically sodium chloride. Notice how we would end up with 2 sodium chlorides, and again, the anion of one with the cation of the other, right? And those are called double replacement or double displacement reactions. Another type that we'll look at is combustion reaction. That's much like the reaction of fuel. Or in this case, what we have is C4H10, which is basically octane, which could be butane actually, which could be found right there. It's butane, right? If it reacts with oxygen gas and heat, it will basically form carbon dioxide, water, and energy. right? Energy could be in the form of heat. So that's an example of combustion reactions, and they're typically carbon-containing compounds that are reacting with oxygen gas. And notice that particular chemical reaction is balanced, right? For every 2 moles of butane, we need 13 moles of oxygen, and it will form 8 moles of carbon, 10 moles of hydrogen, right? If you count the number of atoms on the reactant and the product side, it's balanced, right? We have 4 carbons, and right here, we have 1 carbon. So if we multiply this by 2, then we'll have 8 carbons right here and 8 carbons right there, right? For oxygen, you would probably do it last because you have oxygen right here. And if it's a fraction, then remember, you can multiply everything by a specific value. Okay, we could balance it. Let's try. C4H10 plus O2 goes to carbon dioxide plus water. All right. So remember, start from the left to the right. Keep hydrogen and oxygen for last. So it looks like we have 4 carbons right here. So I'm going to add 4. Okay. And I have 10 hydrogens right here. I only have 2 in the product side, so I'm going to add 5. That's 10 hydrogen in the product, 10 hydrogens in the reactant, 4 carbons in the product, 4 carbons in the reactant. So I'm only left with oxygen. Okay, so here I have 4 times 2, 8 oxygens. Right here, I have 5 times 1, or 5 oxygens. So overall, I have 13 oxygens in the product side, and I only have 2 oxygens in the reactant side. So what you do to balance it, you put the 13 and you divide by 2. So it's like 13 over 2. And when you do that, to get rid of the fraction, what we need to do is multiply everything by 2. And because of that, we have 2 of octane. 13 divided by 2 times 2 is basically 13. Carbon dioxide becomes 8, and water becomes 10. All right, since we talked about balancing on our last lecture. All right, so again, combustion reaction is a type of reaction where oxygen is basically combining to form 1 or more oxygen-containing compounds, like the combustion of fuel yields carbon dioxide and water. Right? If you have an unknown compound and oxygen is added, it will basically burn, right? And then water will be absorbed, and then carbon dioxide could be absorbed, and then the other substance can actually be separated. Right? If another example of combustion reaction is the combustion really of octane, which is basically a component of gasoline if it reacts with oxygen, right, in the engine, and then carbon dioxide and water is released. Octane basically has the chemical formula C8H18. Okay, that's octane. So this is a summary of the different types of reaction: combination, decomposition, single replacement, double replacement, and combustion reaction. In combination, we have the example here of calcium reacting with chlorine gas to form calcium chloride, right? And in the decomposition, we have iron 3 sulfide reacting or decomposing to form iron and sulfur. And in single replacement, we have carbon reacting with silver nitrate to form silver and copper nitrates. Okay. And in double replacement, we have barium chloride reacting with potassium sulfate to form barium sulfate and potassium chloride. Hopefully you're recognizing cations and anions and how they're swapping. And in combustion, we have methane reacting with oxygen to form carbon dioxide, water vapor, and energy. Right, let's take a look at the single replacement reaction. Right, we have copper, and copper is one of the transition metals, and its charge is variable. We have silver nitrate. Nitrate is one of the polyatomic ions. Okay. So copper is just the metal, right? So it's not like we have an anion and a cation. We just have the pure elements. When we think of silver nitrate, nitrate is one of the polyatomic ions that carries an overall -1 charge. Silver is one of the transition metals that carries a plus charge. And that's why we needed 1 of silver per 1 of nitrates. Now, if you take a look at the product, well, because copper is a metal here and silver is a metal, it's the silver and the copper that are swapping when we think of the single replacement, right? So the silver will become the metal on its own and copper will form copper nitrates. So those 2 brackets, what are they indicating? They're indicating that we have 2 of nitrates. You wouldn't necessarily been able to predict that. That copper would end up being carrying a +2 charge, right? Copper is one of the transition metals that can have variable charges, +1 or +2, all right? But in this case, it's specifically +2, right? And we could tell that because we have 1 copper per 2 nitrates. All right, so now let's take a look at a few examples and decide if each of the following reactions is a combination, decomposition, single replacement, double replacement, or combustion. All right, so pause the video and think about it and then replay. Okay, so let's take a look at the first example. It looks like we have barium on its own, the metal, and it is reacting with nitrogen. And nitrogen is one of the elements that exists in nature as a diatomic molecule, as N2, nitrogen gas. And it looks like both are combining to form a single compound. Right, they're both combining to form a single compound. So that would be an example of combination. It's a combination reactions. 2 or more substances or atoms are combining to form a single product. Okay, so now let's take a look at the second problem. We have silicon oxide reacting with hydrogen fluoride to form silicon, fluoride, and water. What do you guys think? Well, let's consider the problem. Silicon, and here's silicon right here, oxygen. We have oxygen right here. Hydrogen. We have hydrogen right here. And fluorine. We have a fluorine right here. Right? Do you agree that the cation of one is basically being replaced with the anion of the other? But you don't really have cations and anions. Right? We're dealing with non-metals, but it is double displacement or double replacement. Okay, so if we take a look at the next one, we have silver reacting with dihydrogen sulfide to form silver 1 sulfide and hydrogen gas. Notice silver is basically replacing the hydrogen, right? So that would be an example of single replacement. Right? And the example that potassium carbonate, that would be an example of decomposition. And finally, we have methane reacting with oxygen gas, forming carbon dioxide, water, and energy. That would be an example of combustion. All right. So now we're going to take a look at a different type, and it's known as redox reaction or oxidation-reduction reactions. There are many different types of reactions that basically are also classified as redox reactions, but they typically involve the transfer of electrons, all right? And many of the redox reactions actually involve oxygen, and an example was combustion reactions, right? Combustion reactions are one of the different types of reactions, but those are also redox reactions because there's transfer of electrons between the two components or the two reactants. All right. Rusting of iron is one example. We have iron, it reacts with oxygen in it, then it forms iron oxide. Or when hydrogen gas reacts with oxygen to form water vapor. There's also the combustion of octane. Okay, so they're all involving the transfer of electrons. So we call them oxidation-reduction reactions or redox reactions. Right? So electron on a given substance, let's call it A, ends up being transferred to another substance called B. That's an example of a redox reaction. Something or one substance or atom is gaining an electron and the other is losing an electron. Notice A in this case is transferring the electron, so it's losing an electron. If something loses an electron, it's said to be oxidized, right? So if something loses an electron, something else has to gain an electron. And in this case, B is the one that gained the electron. So now B has the electron. So B is reduced, right? Reduction is the gain of electron. So we say that A is oxidized, it lost an electron. So, and B is reduced, it gained an electron. So we call it oxidation-reduction reactions, right? One way to remember it is by oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Okay, so how can we identify if something lost or gained an electron? Well, we write what we call half reactions, okay? Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay, well, what would we expect to gain or lose electrons if you're between, like, let's say sodium and chlorine? Well, sodium is a metal, right? Chlorine is a non-metal. Non-metals have higher ionization energy. They tend to attract electrons more. It requires more energy to remove an electron from a non-metal. So just like non-metals tend to form anions, in this case, it's being also the one that is reduced, right? So let's take a look. We have sodium. Sodium becomes sodium positively charged, so lost an electron. You have two chlorine. Each one is gaining one electron, so you have two chlorine ions. Okay, so when sodium metal reacts with chlorine gas to form sodium chloride, that's actually an example of a combination reaction, right? If you think about it, that would be an example of a combination reaction. But it's also a redox reaction. There's oxidation and reduction taking place. Now, what is being oxidized and what is being reduced? Sodium is losing an electron. So sodium is said to be oxidized. Chlorine is gaining an electron. So chlorine is reduced. So the top reaction, we call it the oxidation half reaction. And the bottom one, we call it the reduction half reaction, right? So be able to recognize them. Okay. We're going to come back to something similar, but here is the example showing you sodium metal right here. In a container that has chlorine gas, they'll react, electrons are being transferred, sodium loses its electron, chlorine gains an electron, and then you form sodium chloride. It's an ionic compound, so it's basically a crystalline lattice structure. We have sodium surrounded by chlorine ions and so forth, right? So we have sodium chloride, an example of a redox or oxidation-reduction reaction. Another example, if we have a solution of calcium sulfate, right, in water, it's blue. And then if we go in and we put a strip of zinc, then a redox reaction will take place. So if you think about it, calcium is in group 2A and carries a +2 charge. Sulfate is one of the polyatomic ions with a -2 charge. Zinc is a metal, right? But zinc is one of the transition metals that carries a +2 charge. Okay, so let's take a look at what happens when you put the zinc in that copper sulfate solution. What you have now are those copper ions in solution, right? Or the I'm sorry, I wrote calcium. Copper ions in solution. It's copper sulfate, all right? Copper ions in solution. And the redox reaction is going to take place between copper and zinc. Zinc metal, it has an oxidation state of 0. But in solution, when it reacts with copper, notice what is happening. Copper is gaining an electron, whereas zinc is losing 2 electrons. So then copper will basically coat that metal zinc strip, and zinc will be released in solution. So you'll actually end up seeing this coating on the zinc strip because of the redox reaction, where zinc is being oxidized to zinc ion and copper is being reduced to just the pure metal with an oxidation state of 0. So now, is there a way to assign those oxidation numbers when something is being oxidized or reduced? Like when we saw the example of sodium, how do I know that sodium to sodium ion plus an electron is really not showing charge, but rather oxidation state? Well, for non-metals, for fluorine, which is in group 7A, its oxidation state is -1, similar to its charge when it's an ion. Hydrogen is a +1, oxygen, which is in 6A, is a -2, again, similar to its ionic charge. Notice group 7A, 6A, 5A elements, they're similar to their ionic charge, all right? So they're really also based on the electron assignment. All right, so how can we differentiate between ionic charge and oxidation state? We actually write them differently, right? When we put the number followed by the negative charge, then we're thinking of the ions gaining and losing electrons. When we include the negative charge or the plus charge first, then we're referring to oxidation state. Okay. So if we are dealing with a neutral molecule, its oxidation state is always going to be 0. So for instance, oxygen gas exists in nature as oxygen gas, as a diatomic molecule. So its oxidation state is 0. If you have zinc, just the metal on its own, its oxidation state is also 0. Okay. If you have a polyatomic ion, such as nitrate or sulfate, its oxidation state is equal to the charge of the ion. So nitrate has an oxidation state of -1, sulfate has an oxidation state of -2. Okay, well, that's what I covered earlier. If you have a molecule that is overall or if you think of an overall molecule, the net sum of oxidation states is 0. Much like when we think of a molecule, its net charge is overall 0. If you go back to here, it's like sodium chloride. Although sodium is positively charged and chlorine is negative, overall there is 0. So when we think of oxidation state is similar, right? If the molecule is overall neutral, the sum of all oxidation states will have to equal to 0 as well. Right, here are some examples of like diatomic and polyatomic elements, or that exist as diatomic or polyatomic molecules. Right? If we're dealing with just the elements on their own, like chlorine, let's say, or magnesium, the oxidation state is equal to the charge. And we know magnesium typically is in group 2A and carries a +2 charge. So it has an oxidation state of +2. Chlorine has an oxidation state of -1, right? So metals tend to have positive oxidation states. Group 1A, group 2A are +1 and +2. Non-metals tend to have negative oxidation states, similar to the fact that non-metals form anions. Okay, so we have chlorine. What would be the oxidation state of chlorine gas? It's a free diatomic element. It exists in nature as chlorine gas, so its oxidation state is 0. Right, what about carbon dioxide? Well, carbon is in group 4A. Oxygen is in group 6A, and we have 2 oxygens. So if each oxygen is a -2, carbon is a +4, because the sum has to be 0. So oxygen is assigned a -2, so then carbon has to be a +4, because the sum has to be 0. Okay, what about potassium oxide? Actually, this one has a typo. This 2 shouldn't be here. Okay. So the sum has to be 0. Some typo. Okay. Pretty sure this is a typo. This has to be potassium as in group 2A. So we need 2 potassium per 1 oxygen. So we have 2 potassiums per 1 oxygen. Okay. Okay, so potassium fluoride. Again, fluorine is in group 7A, assigned a -1. Potassium has to be a +1, right? So the overall oxidation state is 0, but fluorine is a -1 and potassium is a +1. I mean, a fluorine is a -1. Now, sulfate is a polyatomic ion, so the sum has to be -2 overall, all right? The sum has to be -2. So you have 4 oxygens. You have 4 oxygens, and each oxygen has to be a -2. So that's overall -8. Okay, so we're going to assign oxygen a -2. And you have 4 oxygens, so that's -8, and we have 1 sulfur, and we want overall the charge to be a -2. So then sulfur has to be a +6, right? Again, this is oxidation state and not charge, right? So then oxygen is a -2 and sulfur is a +6. Oxygen will always be a -2, right? Although oxygen and sulfur are in the same group in the periodic table, oxygen will always be a -2 when you're assigning oxidation state, right? And then assign the other elements based on the total or the net oxidation states. Right? Now let's consider the reaction between carbon and sulfur. Okay, what's being oxidized and what's being reduced? Can you assign the oxidation states? Okay, well, carbon and sulfur in this case are both the pure elements, right? So their oxidation state is 0. Sulfur, we have 2 sulfurs per 1 carbon. Sulfur is a group 6A element, so its oxidation state is typically -2. Notice, unless it was combined with oxygen. Okay, so we have 2 of sulfur, so then overall it's a -4. Okay, so each sulfur is a -2. And the sum of all the oxidation state must be 0, so carbon must be 4. Right? All right, remember, oxidation is the loss of electrons and reduction is the gain of electrons. So carbon, so you take a look at the oxidation state of the same atom in the reactant side and in the product side, and sulfur in the reactant side and then in the product side. Then you assign it. If it's the pure element on its own, whether it's a diatomic molecule like hydrogen, nitrogen, oxygen gas, or group 7A elements, remember those are diatomic. They exist in nature as like bromine gas, fluorine gas, oxygen gas, chlorine gas, nitrogen gas, hydrogen gas. You'd assign those an oxidation state of 0, or like if you just have zinc or just magnesium, all right? And then when you look at the product, the net charge or the net oxidation state should be 0. All right, unless we're dealing with a polyatomic ion. All right, well, I hope this was helpful. I will see you next time.